Okay, so let us start with the insertion sort. Basically, insertion sort is a very simple sorting algorithm that works iteratively, inserting each element of an unsorted array in a correct position at sorted array. Okay, so in this algorithm we always start from the second element of the array, right? We start with the second element of the array, right? As right, first element is assumed to be sorted. Okay, we will assume, right, the first element is already sorted. Next step, what we will do is we will compare second element, right? We will compare second element with, right, first element and check if second element is smaller than smaller. Then swap them. Okay, then swap them. After that, move to the third element, right? Compare it with first two elements. Okay, compare it with first two elements, right? Same procedure which keeps on, right, getting repeated. So repeat till entire array is sorted. Repeat till entire array is sorted. Okay, so this is the basic algorithm. We will look at it in a pictorial way as well. Okay, first let us understand the time complexity of this algorithm. Okay, so time complexity, right? Basically, time complexity is measured in different situations. One is called as best case. Best case means, right, if the array is, right, almost sorted. Okay, almost it is sorted. In that case, the time complexity will be big O of n, right? In the best, sorry, in the best case, right, if the array is almost sorted, then it will work in O of n time, right? The next case is average case. What happens with the average case here? It will be big O of n square, right? It will be big O of n square. If the elements, right, are randomly organized, in that case it will be O of n square. Worst case, right? Worst case, if the array is in reverse order. If you want to do ascending order, but all the elements are in a descending order, in that case again the time complexity will be big O of n square, right? So these are the different situations. So you need to understand when is the best situation to use a insertion sort, right? So insertion sort is always best when you are using it for, right, when the array is almost sorted. That time it will work faster, right? Now let's look at the advantages, right? There are a lot of advantages of this one. Always the first statement is simple and easy to implement. For students this becomes right, this sentence becomes like a statement to fill the pages. And also it is stable sorting technique, so this will not create a problem for duplicate elements, right? Okay, it's a stable selection. Okay, next, efficient for efficient for small set of data, right? And nearly or sorted almost sorted. Then then space efficient. Space efficient, it won't take much, or we can call it as a in place algorithm, right? It doesn't take much space, because the auxiliary space it uses is auxiliary O of 1. Okay, so we just need one extra temporary variable. Okay, next, and also there is something we call it as adaptive, right? Okay, it is very adaptive. So basically number of inversions is directly proportional to the swap, right? Okay, so it's like a depends, situation based, as we have seen this best case, worst case, and average case. If the array is almost sorted, then it will get sorted in a very less time. If the array is completely in the reverse order, it will take a too much of time. That is why we call it as adaptive nature. It is called as adaptive nature. Okay, now disadvantages. Okay, if any spelling mistakes are there, I'm sorry on it. Okay, inefficient for large data set. Okay, it is inefficient for large data set, means if you have a lot of data that needs to be sorted, then this sorting technique is not suitable, right? And it is not as efficient as quick and merge sorts, because in most of the cases we prefer using quick and merge sort. These will be the most efficient in almost every cases, right? In most of the cases they will be, right, used. Okay, now let's look at what are the applications, because in the first two, bubble sort and selection sort, we don't have any application because we hardly use it, right? So the applications are, right, when the data set is small or merely sorted. Okay, right, and it is also simply, right, simple, right, and stable. Okay, so basically it is used in a bucket sort as subroutine, right? It is used in bucket sort as a sub, it acts as a small part in the bucket sort, right? Okay, okay, and also it is used in hybrid sorting algorithms, right? It is used in hybrid sorting algorithms. For example, um, right, generally this is mixed with, if I have to tell you, it is usually mixed with quick or merge sort, right? It is mixed with a quick or merge sort techniques, right, when the sub array size becomes very small, right? Okay, for, or you can take the examples as trim sort, right? Trim sort, right? Or there is something called as intro sort. So the, when you have these kind of sorting techniques, in that situation we use this insertion sort, and we mix them with a merge and quick sort whenever the data set is small, and I want to do it in an efficient way and in the quickest way. That time we can club insertion sort either with a quick sort or merge sort. Okay. Generally trim sort and intro sort, these kind of additional sorting techniques are there. We use them in such situations. Okay. Now let's look at a pictorial representation of how does the array works. Okay. Let's look at pictorial representation. Insertion sort. Okay. Insertion sort. Okay. Now as I've told you that in insertion sort, right, let us take certain elements into the array. Let's take certain elements into an array. Sorry. Okay. Let us consider 5 elements. Okay. And let the element be 23, 1, 10, 5 and 2. Right. This is the initial status of the array. Right. Now what we will do is we will start from 1 second. We will, as I've told you, that we will start from the second element, right? We will start from the second element and we will assume the first element. We will assume the first element is already sorted. We will assume the first element is already sorted, right? This is what we will assume it as. Okay. Now what we will do is in the first pass. Now in the first pass, right? What we will do, right? In the first pass, 1 second. I'll copy these things, entire thing, so that I don't have to write them again. Duplicate, copy it, keep it here. Okay. Now in the first pass, what we will do is we will compare the second element with the first element. So if the second element is smaller, then we will swap them. If I swap them, this will become 20, sorry, this will become 1 and this will become 23. Now I can say that the array, 2 elements in the array are sorted. As of now, 2 elements in the array are sorted. Sorry. Okay. As of now, 2 elements in the array are sorted. Okay. Now what I will do, I will go with the second pass. Now I'll go with the second pass. Okay. Now in second pass, what we will do, right? Now we will compare the third element, right? Now we will compare the third element with the first 2 elements. Now we will compare third element with the first 2 elements. So here the elements in the second pass are 1 and 23. So we will compare 10 with 23 and 1 both. So as you can see that, right, the element will get sorted like this, right? So 1 will remain as it is, right? 10 and 23 will get swapped. 10 and 23 will get swapped, or you can say that they get shifted. Now after this, you can see that the 3 elements are sorted, right? After the second pass, you can see 3 elements are sorted. Now similarly, we will keep on repeating this till the last element. We will keep on repeating this till the last element. So let's start with the third pass, right? We'll start with the third pass. In the third pass, right, these are the elements what we have in the third pass. Now 5 will be compared, right, till here. 5 will be compared till this point, 10 and 23, because the 1 is already, right, 1 is already, right, in place. 1 is already in place. So 5 will be compared with 10 and 23. 5 will be compared with 10 and 23. So till that time it will compare, right? Now you will shift all the elements and insert the 5 at the right place. Then this will become 10 and this will become 23, right? So now you can say that 4 elements are in place and they are sorted. Now what we will do, we will go with a fourth pass. Now in the fourth pass what we will do, we'll repeat all the steps, right? We will repeat all the steps in the fourth pass. One second, I'll just write down this. Okay. Now in the fourth pass, the elements are in the fourth pass elements are 1, 5, 10, 23. Now you will compare this last element with previous elements and it will trace back to the correct location till here. Now what you will do, now you will insert that 2 in the right place. So now the array becomes 1, 2, 5, 10, 23. So after this you can say that the entire array is sorted. Now you can say that entire array is sorted. So what we will do for doing this is, we will take the first element and we will keep on comparing it with the previous, and we identify the position where it needs to be inserted, right? We identify the position where it needs to be inserted. Okay, that's how we go on doing it. Let's try to write a code. Have you understood this part? If yes, we'll go for the code. Sorry. Now I is currently, I'm taking a sample input and I is currently at index 4, and j will be what? J will be I minus 1, which is 3. And what is the key element? Key element is equal to 2. Okay. Now what I will do in the while loop is, I will compare, right? One second. ARR of j plus 1 is equal to ARR of j. Now I will compare if this current element, my condition is what? If ARR of j is greater than key element, this is my condition. So 23 is greater than 2. If it is true, then shift the element here. How do you shift? J value is 3. So 3 plus 1 is 4 and this is index 3. So shift the element from index 3 to index 4. 23 is shifted. Now decrement j value becomes 2. Now you will compare 10 with 2. So again this will also be shifted. This will also be shifted, right? So 10 gets shifted here. After that j gets decremented, it becomes 1. Then you will compare 5 with 2. You will compare 5 with 2. Now what will happen here? 5 is greater than 2. Then again you will shift the element here. So this element gets shifted. So 5 will come down in this place. Okay. After that, j value gets decremented, it becomes 0. Now when you are at index 0, the element is 1. 1 greater than 2, false. Condition becomes false. So j value is how much here? 0. Condition is false. Now what will happen? You will come out of a loop and insert ARR of j plus 1 is equal to key. Insert the key at one position ahead. As j is 0, 0 plus 1 is 1. So at this index, I'm sorry, at this index, the key element will get inserted. Are you understanding now? So based on this only, we have written the code here, right? We have written the code here. You took the current element into key, and this will keep a track of previous indexes, and this is used for shifting the elements till we find the correct position, right? Till we find the correct position. And once you come out of the loop, you got the position, then insert the key element at the right place. So this is all about, right, insertion sort. I hope you have understood. If you have any doubts, you can ask.